All right, we have plenty of time for jokes. Let's do some jokes. All right, let's see which ones I have here. All right, so a light wave walks into a bar at a high frequency and says, "Ouch, that hurts." Hurts, you know. But I mean, someone should have hit it or something. But still, good. I especially appreciate the home-brewed jokes, although you can certainly send any that you find anywhere else. A few are relevant for later on, so I won't, well, I'll read some anyway. How does the solar system hold up its pants? With an asteroid belt. Why didn't the dog star laugh at the joke? It was too serious. Serious is the dog star. I'll show it to you one of these days. Okay. Yeah, all right. All right. What do you call a crazy spaceman? An astronut. I'm not getting too many laughs here, folks. All right. What kind of light goes around the Earth? A satellite. Oh, these are bad. What did Saturn say to Jupiter when he asked if he could call her? Don't call me, I'll give you a ring. Oh, my. Okay. What is an astronomical unit? One hell of a big apartment. An astronomical unit, get it? All right. Okay, there's a few others. Well, okay, I'll read this one, even though it actually is more relevant in a couple of lectures later this week. Where did it go? No, I might as well read it when it's most relevant. Okay, I'll read it when it's most relevant. All right, let's get started here. There's a lot to cover. Oh, somehow I ended up with a Chico's Mexican restaurant, the best pizza in town photo. The owner of this is welcome to pick it up after class. Anyway, Chico's Mexican restaurant. All right, couple of announcements. First of all, it's my mother's birthday, so I wanted to wish her a happy birthday if she's out there in Electron land. Thank you, Mom, for whatever you did to, well, I know what you did, but thank you for giving me a chance in life and making me grow up to be okay, I guess, according to some standards. All right, quiz. She might be watching in Electron on land, I'm not sure. So quiz this week. A couple of people have asked about the format. It won't be true, false, and multiple choice because we do that on the midterms and the final. So this will be more of a chance for you to answer short questions, work out a simple problem, explain a concept, or deduce something from something that we've taught. I told you that I like having you figure out, for example, what the phases of, when a particular phase of the moon might be visible and where in the sky, that kind of thing. All right? And then some people have asked about getting in touch with their GSIs. All of their email addresses are on BSpace under resources, I believe. Okay? So please don't email me. If I get 750 emails, what's my GSI's email? Then I won't be able to have time to answer the really good questions of content that do frequently come to me, and I do try to answer most of them. Homework 3, due this Friday. Star parties tonight, Tuesday, and Wednesday. The sun is setting earlier each day for reasons I'm sure you know, but we'll go over them again today. The seasons are changing, so we will start earlier now, 8 o'clock till 9 o'clock. And if there's a lot of interest, we'll continue further than that. But if you want to be guaranteed to see an object, show up before 9 o'clock. And then to make up for all the time that I was gone, I'm holding a bunch of extra office hours this week in addition to my normal office hours. So basically before class on Wednesday and Friday, as well as the usual after class. And also after class today, as usual. Okay? So those will be my office hours this week. Might be particularly useful for those of you who have a discussion section later in the week and want to have some questions about quiz topics and stuff. Okay, and then a bunch of people have already turned in their submissions for this optional Lick Observatory essay or whatever it is you want to give me contest. Give me the stuff by 5 p.m. today. You can find me in my office, 439 Campbell Hall, if you don't have the thing quite ready to give to me after class. And again, this is completely optional. Okay? Now, in my office hours, I have found that there's considerable confusion still about absorption and emission lines, and in particular, some confusion regarding the very interesting demo that was shown in your discussion sections last week. So I thought I'd take 5 minutes to explain again a little bit what we were doing and to point out something important that I didn't really emphasize in class, but is relevant to the actual demo that was being shown in your discussion sections. And I think most GSIs covered this, maybe some forgot to, but in any case, it's hard enough that I might as well mention something specific here in lecture. So what I did discuss extensively is how if you have a whole bunch of photons streaming along toward an atom of gas, then if there's an electron in the right energy level and if there's an appropriate energy level above it, then one of these photons could get absorbed, in this case the green one, exciting the electron from, in this case, the second energy level to the fourth energy level. And so now the green one is missing, and if you were to look at a spectrum of a star or a flashlight that emitted all this light, you would notice an absorption line somewhere in the green part of the spectrum. So that I discussed in some detail. And I also mentioned that once the electron is up in the upper level, electrons are lazy creatures. They quickly like to zip back down to a lower level. Not necessarily the same level from which they started, but any old level, sometimes a succession, a cascade of levels, and that produces an emission photon. And so if you were looking at a spectrum of the gas from this direction, you would see an emission line. And indeed, here's a cloud of cool gas through which you're observing a hot star in this direction, and you would see an absorption line produced by hydrogen atoms in that cloud of cool gas. But viewed from other directions, that is not directions along the line of sight to that hot star, you would see the emission lines that are emitted, the photons that are emitted by this cloud of gas in random directions. I had mentioned that this emission can occur in any direction, any random direction, not necessarily in the same direction in which the photon was going to begin with. So that's, you observe clouds of gas like this, and they emit emission lines. And I'll discuss this more later, but a very famous example of such an emission nebula is the Orion Nebula in the Sword of Orion. There's a bunch of hot stars here. Turns out they're ionizing and exciting the gas around them. And then the electrons come zapping back down to lower energy levels, and they emit these emission lines, okay? So then the question came up repeatedly in my office hours, what was it exactly that you were observing when you looked at those gas discharge tubes in discussion section last week? Remember that? Those were emission lines that you were observing. So your tubes looked something like this. I didn't have a chance to go and photograph the actual tubes that you used, so I found a picture on the internet. So these tubes had low-density gases of various sorts. And in this particular case, the excitation was different from what I was discussing here. Instead of photons being absorbed by electrons, kicking them up into higher energy levels, and then having those electrons come back down, instead there was a different way of getting the electron up to the higher energy level. And that method is through collisions. And I think I briefly discussed this in class where I had someone in the front row kick me, and I said that one way that electrons can get up to higher energy levels is by being kicked by free electrons that are just kind of wandering around. So in other words, you don't have to have absorption of photons, although the main content, the main subject of the lecture a week and a half ago or so was the absorption of photons, because that typically tells you more. But anyway, you can have this collisional excitation up to upper levels. And between two electrodes here, there's a voltage applied, and so there's a a current flowing through wires that are connected to a battery or a power source to either end of this tube here. And what happens is some free electrons that happen to be inside the gas get accelerated along the tube because there's a voltage drop across the tube. And those electrons can hit atoms in that tube, kicking the electrons from lower energy levels to higher energy levels. So those electrons bound to the atoms absorb some of the energy of the free electron and get kicked through a collision up to a higher energy level. So this is a collisional excitation, all right, rather than a photo excitation, rather than absorption of a photon. And once the electrons are up in this higher energy level, they can then jump back down. And in so doing, they emit photons, producing emission lines. So you were seeing emission lines being produced by electrons jumping from higher energy levels to lower energy levels. But the way in which the electrons got to the higher energy levels in the first place was by experiencing a kick in this low density gas because of this current running through it, essentially. The energy is from the current. They didn't get excited up to there by absorbing a photon. So you were seeing emission lines. And in particular, we said that different kinds of gases produce different emission line patterns. And it's the same kinds of patterns as with the absorption lines. So you still have a beautiful fingerprint of what it is you're looking at, but it's an emission line fingerprint rather than an absorption line fingerprint. You know, in 40 lectures, there's only so much you can cover, so I chose not to go into emission lines all that much. You know, I want to move on to other things, but there were so many questions on this that I thought it would be useful to mention this. So here's hydrogen, for example. It has a red line, a green line, and then it's a bit hard to see, but there's a blue one down here. Kind of hard to see, bluish-violet. Helium looks different, sodium, mercury, and so on. And I hope you saw several examples of that in your discussion sections. So these discharge tubes are what you see when you see neon lights, for example, glowing in Reno or Las Vegas, or in a sign that says Experience Physics, which I found on the web. This was done at Syracuse University. And this particular one was a neon lamp. It produces a lot of orange and red emission lines. And this is mercury. It tends to produce a lot of blue ones. You actually don't see them here. I don't see a bunch of blue ones. They might be too faint to see here. But anyway, certain ionization stages of mercury do produce blue lines. And I must admit, I'm a little bit confused as to why I'm not seeing them there. Might be a different excitation state or ionization level of mercury. But anyway, and these were just some fluorescent lights here that were used to produce electromagnetic wave, you know. But here's one of these discharge tubes, and you see them when you look at lights in cities and stuff. They're just gas glowing in a tube along which there's a current going because of a voltage drop between two electrodes. And you don't have to worry about all these things, but enough people asked it that I thought I'd cover it. So here's the hydrogen spectrum. There's the red line, the 3 to 2 transition of the electron. Here's the green line, the 4 to 2 transition. You don't have to memorize that. Here's the blue line, the 5 to 2 transition. That is, these are the Balmer lines, the 3 to 2, 4 to 2, and 5 to 2 transitions, okay? So that's something that any spectroscopist would recognize. And different elements and different ionization stages of different elements produce different patterns of lines. And that's one of the key concepts of the entire semester, because this is how we know what it is that the things out there, stars and nebulae, galaxies, are made of. We take their spectra and see the same patterns of lines as are seen in laboratory gases, okay? Now, on Friday, I hope I'll show you a little demo of this if I can get it all set. Last year, it was kind of dangerous. I almost electrocuted myself and some students in the front row. But you can attach a pickle to a couple of electrodes. Don't do this at home because it's really quite easy to electrocute yourself. Like I said, I almost did it on Friday. And plus, I don't want to do it today or Wednesday because there's a class after hours. And if I short circuit the electronics here, they'll be mad. Whereas there's no class after hours on Friday, and if I short circuit things, well, there's some time to fix it. But anyway, you stick these electrodes into this pickle here, and there's a voltage drop between the two electrodes, and sparks occur, and they excite sodium atoms, which produce these two closely spaced emission lines in the orange-yellow part of the spectrum. And so the thing actually glows. And here's a photograph of one of these guys in case my demo doesn't work. And just to get you to come to class on Friday, I noticed that attendance was a bit low on Friday, and I know it was a nice spring day, actually a nice fall day, but you should try to go if you can to come to class. But anyway, I'll try to show you this. But there's one of these things glowing, and here's an actual video of one of these things, the glowing pickle. Glows on one side more than the other. I need to figure that out. I think it has to do with the direction in which the current is going, so a spark is more likely to occur there. And then I have this really cool thing which has sound as well. So let me take my. All right, I did get an internet connection earlier on. So let me see here.
Where's the light? Here we go.
Yeah. You could say something like that's one hot pickle or something, but anyway. I'll try to get that. I'll try to get it together on Friday. It's a lot of fun to see in real life, especially if sparks occur at the front as they did last year and they almost, catch people in the front row on fire. It was a bit dangerous last year, so I'm not going to do it unless I can figure out how to do it more safely. Okay. All right. 323. Back to solar eclipses. I'm going to tell you a little bit more about them, and then we'll move on. So all of you should watch Friday's lecture because I got a bit animated, I think. I really like solar eclipses, as I think you've all seen now. The total ones are far, 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 far better than the partial ones. I mean, it's, one of these things that should not be missed in life. Like, I don't know, the birth of a baby or a first kiss or snatching victory from the jaws of defeat or something like that. I mean, all these things should not be missed in life, but solar eclipses are among them. Anyway, I did mention that all the partial phases should be viewed through a piece of shade 14 glass. And I had to go and take my car in for servicing this morning, so I couldn't go to the welding store. I'll try to do that by Wednesday or Friday, okay? So I'll get some more of these pieces of glass in case you want one. Totally optional. You can look at the diamond ring effect with your naked eye. You can take the piece of glass off in the last second or two before totality and in the first second or two after totality. That's strictly speaking a partial phase, but it's so little of the sun is visible that it's okay to look at it with your naked eye. But don't look at even this through binoculars or a telescope, because they will collect a lot of light and focus it in on your eye, frying it like boiling it like an egg or something. So basically, rule of thumb, partial phases, use the glass. Totality, don't use the glass, okay? So, but if you're sneaky, you can watch 1 second or 2 seconds of the diamond ring effect with your naked eye. Okay, and here's, I collect T-shirts, and I've been to a lot of eclipses, so here's the great eclipse that I watched in Peru in November of 1994. All right, so let me tell you a few more things. I showed you this path on the Earth, which, is just the projection of the shadow of the moon on the surface of the Earth. So I showed you this photograph, but I inadvertently hid my next slide on Friday. On a curved surface like the Earth, on a spherical surface, if you flatten it out like the Mercator projection of a map, these paths look curved. I mean, they're sort of straight lines on an intrinsically curved surface. So if you flatten them out, they look curved. And this diagram is in the textbook. And a couple of people have asked me why all these things look curved, and that's because you're projecting the shadow on the spherical surface of the Earth, and then you're flattening out this curved surface onto a flat thing like the Mercator projection. So as I said last time, you should definitely, in 10 years, be somewhere along this path from, looks like northern Oregon down to, looks like South Carolina down here. And keep informed before the eclipse as to where the best weather is likely to be, and go where it's likely to be good. Because this will be an easy one for most of you to see unless you're overseas or something by then. And then 7 years later, there's another one that crosses parts of the U.S. and Mexico. There's this amazing convergence in the South Pacific near Tahiti. I like Tahiti, so I'm going to a bunch of these eclipses here. That's really fun. And then my next one actually is this one, August 1st, 2008. I will be right around there where the N is in Mongolia. But it starts here in northern Canada, goes over Greenland and over Siberia down into Mongolia and parts of China. So that's the next one I'll be at, and then I'll be at this one 22nd of July, 2009. I'll actually be in the South Pacific, but it also goes over much of China down here and just south of Japan, starting out in India. So these are all pretty tough places to get to, I understand, but that's why I'm saying definitely see the one in the U.S. And if you do like to travel, you might as well plan your travels around eclipse sites, because you get to see exotic, wonderful places in the world and have the possibility of seeing a total solar eclipse. So if you like to travel, look up on the web where the next eclipses will be and plan your travel around that if you can, afford it and have the time and other things. I know it's hard. I mean, between 1979 and 1991, I saw 0. And since then, I've seen a bunch because I finally have the means by which to do so. But if you ever have a chance, definitely do it. And like I said, I'm going to keep track of all of you. We'll stay in email contact. And if you don't go to this one, especially if you're within 100 miles of it and you didn't take the trouble to go to it, I will retroactively fail you, okay? And if this is the one class that allowed you to squeak by and get a degree at Cal, hopefully not, but maybe, then they will retroactively take away your degree, okay? So it could be very serious, and then you'll lose your job and stuff, and, okay. One other type of eclipse I want to mention, it's called an annular eclipse. It's not that it happens once a year or anything. The annular stands for annulus, and that's basically when the moon, in its elliptical orbit around the Earth, see, the moon doesn't have a circular orbit around the Earth, has an elliptical orbit. So sometimes it's farther away than average, and it's not quite big enough in angular size to cover the disk or photosphere of the sun. Okay, it's a bit too far away, all right? So it doesn't quite cover it. So you get this annulus, and this is just one special case of a partial eclipse. You don't see the corona or anything like that. But as far as special cases go, it is a pretty groovy one, okay? So here's a picture showing you the relative sizes of the moon when it's at its closest in its elliptical orbit and when it's at its farthest away. And again, this phenomenon has nothing to do with the apparently large size of the rising moon near the horizon. That's different. I mean, some days the moon happens to look big near the horizon because it looks especially big because it happens to be especially big. But later on that same night, when its angular size shouldn't have changed much, it'll really appear smaller in the sky. And that's this psychological effect that I discussed last time. But nevertheless, there is this very real effect that sometimes the moon is bigger and sometimes it's smaller. And when it is close to you, it's big, and that tends to give a pretty long total solar eclipse, up to 7 minutes in length. Those are very rare. And when it's far away, you tend not quite to cover the full disk of the sun, so you get an annular eclipse. Okay, so it's under these conditions here that you get an annular eclipse. And here's a progression of photographs that shows you these various stages of the partial phases. And again, it never becomes total. There's a photograph. This is a beautiful one. This one is taken not by me, by Dennis Mamana, I believe in 1991 near San Diego. I was in LA and it was cloudy. It was partly cloudy in San Diego, but there's another photograph I forgot to include. I'll try to remember it for Wednesday. Anyway, so it's a special case of a partial eclipse, but they're kind of fun, okay? But definitely go see totality. Questions about just the general phenomenon? Okay, let me tell you about some of the scientific uses. When we discuss the sun in more detail, I'll talk about how we first studied the corona and the chromosphere, a thin layer, and the prominences during totality. Now there are other ways of studying those things pretty easily. But one of the historically most important scientific uses of total solar eclipses is that they were the first to provide evidence for Einstein's general theory of relativity, new evidence, okay? And it turns out, by today's standards, that evidence is really not very good. But at the time, it made a huge impact on scientists and the public alike. We will study Einstein's general theory of relativity more later on, but basically it's a theory that says that the presence of mass or energy curves or actually warps or bends the actual shape of space and of time in its vicinity. And he had reasons for devising this hypothesis, which later satisfied so many observational constraints that it was elevated to a theory. But one of the first sort of predictions that it made is that there's this warping of space near a mass, and that warping was first measured, though not very well by today's standards, during a total solar eclipse. So it's sort of like a billiard ball on a rubber sheet, which is being pulled down by gravity of the Earth, forming this curved surface. But the analogy fails there because in general relativity, it's the ball itself, not the gravity of the Earth underneath it, that's causing the distorted shape of space. So it's really weird, and we'll discuss it much more later, especially when we get to black holes. But here's how eclipses were used to provide a first experimental or observational confirmation of a new prediction of general relativity. This was the first prediction that was actually confirmed. The idea is this. If you have a star over here and another one over there, and its light is going along like this through space, then when that light is in the vicinity of the sun, it gets bent, just like, light trying to go in a straight line here would get curved from our perspective. Turns out to be a straight line in an intrinsically curved space, but to us it looks curved. I'll talk about all that more later. But anyway, it curves, okay, from our perspective. And a star grazing the sun's limb on the other side would get curved as well. Now, the curving is not sudden like I've drawn it here. It's actually kind of gradual, but I've drawn it sort of discontinuous here just to make it easy to draw the diagram. Now, our eyes don't know that the light was curved along the way. All our eyes know is the direction in which the light entered our pupils, right? We see, okay, the light is coming from over there. We don't know what happened to it along the way. We can't tell. Our eyes can't tell. So you think, forget about the moon for the time being, you think that the star's light is coming from this direction. So although this is the true position of the star in the sky, you think it's displaced from its true position because all you see is the apparent position. That is, the apparent direction from which the light came. And similarly, this star, whose true position here, appears to be over there in the sky. So this was Einstein's prediction, that in the presence of a mass, the apparent positions of stars will be shifted from their true positions. Now, you can take a photograph of the night sky when the sun isn't there at night and get the relative positions of the stars, their various true positions relative to one another. But you might say, how can you ever take a photograph of the same part of the sky when the sun is in the way? I mean, the sky is bright, so how would you do it? There's a clue on that diagram. Yeah, wait until there's a total solar eclipse. The moon conveniently blocks much, though not all, of the sun's light. So the sky darkens. It doesn't become totally dark, but it darkens to some degree, and you can start seeing the brightest stars at least. And so you can take photographs of the brightest stars in a certain region of the sky during a total solar eclipse and compare those photographs in great detail with photographs of the same region of the sky taken when the sun wasn't there and see if there's any shift in the measured positions of stars. Okay? So Sir Arthur Eddington, a British astrophysicist, was the first to do this in 1919. He had 2 eclipse parties, one in Brazil and one off the coast of Africa. And he photographed the sun, and he found that indeed, during the time of an eclipse, the apparent positions of the stars are shifted a little bit away from their true positions. And the closer the star is to grazing the edge of the sun, the greater is this angular shift. See, and the reason for that is that, stars whose true positions are, say, over here. Let's say there's a star whose true position is over here. Its light ray would be going along like this to reach you, and it wouldn't come as close to the sun as, say, this light ray. So it wouldn't experience as much bending, because there's more bending the closer the ray comes to the source of the warping of space, the sun itself. So stars whose light paths are pretty far from the main, from the mass of the sun, don't get bent as much. These stars here, there's a star that didn't get bent much. There's another one whose position didn't get shifted much either. But the ones that were whose true path would have passed close to the edge of the sun get shifted the most. And they all kind of get shifted in a radial direction outward from what would be the direction to the center of the sun. And this was measured by Eddington. It was a very subtle effect. It was a very difficult measurement. Physicists now have reanalyzed Eddington's measurements and have come to the conclusion that, in fact, the data do not unequivocally support the general theory of relativity. To some degree, Eddington was victim to the wishful thinking that all of us have to avoid when we're trying to be completely objective scientists. He wanted relativity to be true. He very much believed in it. And so he kind of interpreted the data, which were marginal at best. He interpreted it to be an unequivocal demonstration of or verification of the prediction of general relativity. And with hindsight, we actually no longer would consider it to be that way. That's not to say there's no evidence for general relativity. There's scads of evidence, much better evidence. But back in 1919, we would say this was not really evidence. Nevertheless, it was announced as evidence for relativity. And here's, by the way, a photograph taken at an Australian eclipse in 1922, where the circles denote the observed positions of stars. You can't see the stars in this reproduction. The quality is kind of low. But they're a little bit shifted from what their true positions would have been. And that experiment was a bit more successful in measuring this effect. Nevertheless, Eddington announced this, and you know, friends of Einstein, like this guy Lorentz, wrote to Einstein, and this is in German, but the translation is, "Dear Mother," this is from Einstein, "I have good news for you today. H.A. Lorentz has cabled to say that the English expedition has really proved that light is deviated or bent by the sun." And this turned Einstein into an overnight sensation. He was already very famous among physicists, but not so among the general public. Okay, but here, overnight, he became like just the greatest scientist ever, perhaps since Newton, or maybe let's say the physicist. You know, I mean, you can argue about biology and chemistry and stuff, but the greatest physicist since Newton. Lights all askew in the heavens, men of science and women, but there weren't that many women doing astrophysics back then, unfortunately. Men of science more or less agog over results of eclipse observations. And there's more, you know, Einstein's theory triumphs, stars not where they seemed or calculated to be, but nobody need worry. You know, there's a book for 12 wise men. Well, Eddington was a pretty arrogant guy, and when one reporter asked him whether it's true that what the reporter had heard was that only 3 people in the world understand general relativity, supposedly Eddington thought for a moment and said, I can't think who the third one would be. In other words, Einstein understood it, and Eddington understood it, and according to Eddington, no one else in the world understood relativity. Now lots of people understand it. I'll tell you the basic principles later on, but anyway, no more in all the world could comprehend it. Well, baloney, but anyway, you know. But it was really quite a historically important event, even though by today's standards, it would not be considered very definitive proof or evidence for relativity, okay? However, as I write here, subsequent, much more accurate tests have verified the predictions of general relativity to many decimal places under a wide degree of circumstances. That doesn't mean general relativity is true. We never know truth. In science, we're always trying to get a progressively better description or model of how the universe works. We don't know whether that's the truth. The truth is for mathematicians or perhaps theologians or philosophers, although I would claim their own truth is as they view it themselves. You know, I don't know that we can ever come to any absolute truth. But science is trying to get a progressively better model or description of the universe. And as a model, general relativity works extremely well. Where it fails is where it tries to describe things that are very small, the arena of quantum physics. But where quantum physics and general relativity both fail is when you consider a large amount of mass in a very small volume, like the singularity in the middle of a black hole or the birth of the universe. We'll get into this later, but this is why physicists are now trying to devise a so-called theory of everything, and some of you have heard of string theories or superstring theories. I'll tell you more about them later. Everyone admits that general relativity and quantum physics are incomplete, but both of them work very, very well in their respective domains of applicability. General relativity on the very large, quantum physics on the very small scales and with small masses. Okay? Questions? All right. I'm sure there's a lot of confusion about relativity, but that's okay. Come to my office hours, and in particular, we'll study it in more detail later. I just wanted to give you this historical little tidbit. Total lunar eclipses, very quickly, because we've encountered them already this semester, but the moon goes into the sun, into the shadow cast by the Earth, okay, and gets dark. All right, so you can watch that, and interestingly, if you photograph it like this, you can see that these two arcs trace out the outline of a circle. And every single lunar eclipse, you find that the shadow of the Earth is circular. And this was one of the early pieces of evidence that the ancient Greeks used to deduce that the Earth is basically a sphere. Because no other shape always casts a circular shadow regardless of how you look at it, okay, regardless of how the sunlight is falling. So this was, the Greeks figured this out quite long ago, over 2,000 years ago, in fact. So there's the partial phases, and many of you saw the total lunar eclipse. It was really a wonderful sight to see. I've discussed this a little bit already, but just to formally address it, the moon is not completely dark during an eclipse because some of the sun's rays don't get blocked by the Earth. Rather, they go through Earth's atmosphere, and Earth's atmosphere bends them, just like a piece of glass or a raindrop can bend water, can bend light because the light slows down in these substances. So too, light slows down an eensy-weensy bit in the atmosphere of the Earth, and that, when you consider the interactions of the light with the air, causes it to bend. So a little bit bends around the Earth, striking the moon. But the predominant color that reaches the moon is orange or red or some shade of yellow, okay? Because, as in the case of the setting and rising sun, the blues and the greens and the violets are both scattered or reflected out by the Earth's atmosphere, thus preventing them from getting to the moon, or they're absorbed by dust and smog and particles in the Earth's atmosphere, further deepening the reddish-orange color of the red, so of the light of the moon. So it's really both of these effects, and it also depends on whether the moon goes through the center of the Earth's shadow or only near the edge. Sometimes it only barely gets into the Earth's shadow, so it's relatively easy for light rays to bend around a little bit. The eclipse we had this past August was a very deep eclipse. The moon went almost through the center of the Earth's shadow. There's also a lot of junk in the air. There's a bunch of fires going on at that time and stuff. So that was a pretty darn dark eclipse. It might have been the darkest one I've ever seen, actually. And you should go back to slide number 56 to understand then why both the setting and rising sun and the eclipsed moon appear orange or red. Now, important point. This stems all the way back to lecture 1, where I think Brett, answered the question of why I see a little bit of the moon during the moon's crescent phase. He said, I think, that this was the light bending around. If this were an eclipse of the moon, I would agree. That's the reason why we see the dark side of the moon. I don't know if Pink Floyd knew that, but this isn't an eclipse. This is a crescent moon caused by the changing geometry of the Earth, Moon, Sun system. And you should remember that, or be able to figure out that during a crescent phase of the moon, they, on the moon, would see what phase on Earth? A gibbous, right. Just think of it. You're standing here, and you're seeing the side of the Earth, this right-hand side that faces you. So it's mostly a lit-up thing. So light gets reflected off of the Earth, goes back to the moon, reflects off of the dark side of the moon, and then comes back to the Earth. That's that phenomenon called earthshine that you see during the crescent phase of the moon. That's different from the reason that the moon is lit up during a lunar eclipse, and you should understand that reason. Okay? And then finally, as I mentioned last week, eclipses, both lunar and solar, don't occur every month. And this time I did remember to bring my Earth. So here's the sun. Put it up here, perhaps. Rolls. And it's going down the warping. Shoot. This microphone. The microphone will probably roll as well. Here, I'll put it down here. So here's the Earth. And the moon, and the Earth is going around the sun in some plane. But the moon doesn't orbit the Earth in exactly the same plane as the Earth orbits the sun. Rather, the moon is tilted by 5 degrees. So if it were exactly coincident, if the planes were exactly coincident, you'd basically get a lunar and solar eclipse pretty much once a month. A lunar eclipse in that position and a solar eclipse in this position, okay? But because it's tilted, usually the moon isn't exactly collinear with the sun when it's new, and not exactly collinear with the sun and the Earth when it's full. And so the shadow of the Earth misses it, or the shadow of the moon misses the Earth. So you don't get an eclipse. But if I go a quarter of the year, if I go a quarter, let me tilt it. Keep your tilts the same. It's hard to do. Got to remember lots of things here. You go a quarter of the year later, notice that now when the moon is over here, gravity, can't live it with it, can't live without it. So anyway, it can be collinear if it weren't moving. I should chew some gum right before lecture, and then, okay, and then over here it can do the same thing, because this tilted plane does cross the orbital plane of the Earth around the sun in 2 positions, there and there, and occasionally at some times of the year, those things, can be collinear. However, you don't always get an eclipse even at those times, because the moon isn't necessarily there or there at the time when the geometry is right for producing an eclipse. So eclipses tend to be pretty rare. Total solar eclipses maybe once every year and a half. Total lunar eclipses about as frequent. The partial ones are observed much more frequently than that. Up to 7 times per year is the maximum. But the total lunar eclipses are much more readily observable by a large population on Earth than the total solar eclipses are. Because you see, anyone on the dark side of the Earth, that is, anyone who would see a full moon at this moment, which is anyone on the dark side of the Earth, would see a fully eclipsed moon, right? Whereas only those people who are on this small little spot on Earth where the shadow of the moon happens to reach the Earth, only those people would see a total solar eclipse. That's a very small fraction of the Earth. Remember the little paths along the Earth? It's a very small fraction of the area of the Earth compared to the large area of the Earth, half, that could see the total lunar eclipse. In fact, more than half of the Earth can see a total lunar eclipse at any given eclipse, because the totality lasts over an hour, and so parts that were in the daytime side during the beginning of the eclipse rotate into the nighttime side sometime during totality. So in fact, slightly more than half of the Earth's surface is exposed to a total lunar eclipse every time one happens. So the chances of you seeing one are reasonably high, and indeed, we had this one at the beginning of the semester. All right. But to see the total solar one, you probably have to travel, unless you're lucky, because any typical place on Earth gets visited at random by a total solar eclipse, something like every 360 or 380 years. Okay, so you have to travel typically to see a total solar eclipse. They're not going to come visit you unless you're lucky. Okay? So obviously, having seen 8 of them, I haven't just taken flights at random to random places on Earth. I know where to go. And this is all on the internet. You can find eclipses that tell you exactly when and where eclipses will be. I'll give you a few websites on an email blast later this week. Okay? Questions? That pretty much finishes eclipses. Michael? The phases of the moon slide. Okay, question regarding that. Yeah. Why do these not have more darkness? Or The ones in the square. Oh, these. Yeah, that's just because the publisher drew it as a shade of gray. Yeah. The right-hand side, the purely white side, is the lit up side. No, yeah. This should be totally black. They should have drawn it as a little dotted line here to show the outline of the moon. You're absolutely right. Those parts are completely dark except for the slight earth shine, okay? They should not be as bright as is shown in this slide. Yeah, absolutely, okay? Yeah. By the way, the earth shine decreases as the phase of the moon gets bigger for two reasons. First of all, the part that's lit up and that you see becomes brighter and brighter, overwhelming the dim light of the earth shine. And secondly, what's the other effect that actually makes the light of the earth shine itself be less and less? Not just a contrast effect, but the earth shine light itself becomes progressively less as the moon orbits the earth. And why is that? Absolutely. Who said that? What's your name? Eve. Eve says, because less and less of the earth from the moon's perspective is being lit up. Here I said that the earth is gibbous from the perspective of the moon. What is it at this lunar phase? Quarter, yeah, or half lit up from our perspective. What is it from the waxing gibbous phase of the moon as seen from Earth? Yeah, it's crescent. What kind of a crescent? A waning crescent, that's right. So there's less and less light reflecting from the Earth going back to the moon. So you typically see the Earth shine only in the early crescent phases like this. Okay, good question. So now, oh my Lord, 3:53. Okay, I'm a little bit behind schedule, but it's not too bad. Let me tell you a little bit about some other celestial phenomena. The sky is divided into groupings, fairly familiar groupings of stars that we call constellations. And they're largely of Greek origin, although there are ones from other cultures as well. But many of the names that we use are the Greek names, and there's 88 of them, and they're pretty arbitrary. Typically, the stars of a constellation, like Cassiopeia, this W here, are not at all physically associated with one another. They're not bound to each other. They don't know about each other in any physical way. Indeed, you can see these 5 stars, Alpha, Beta, Gamma, Delta, and Epsilon, are really at very different distances from the Earth. So this is not a physically bound collection of stars. It has no physical relevance whatsoever, basically. And this is the fundamental reason that most professional astronomers don't even care about constellations, much less caring about astrology, which has no scientific statistical evidence whatsoever. Where Mars is, the day that, the moment you were born, appears to have absolutely, truly no effect on your life. It's fun to read the horoscope and all that, but look, don't believe it, okay? That's astrology. But even the constellations themselves are not particularly physically meaningful. Now, we always get asked by reporters, what constellation was the black hole that you discovered in? And we have to go and look it up, We don't really know in general because it doesn't matter. So these stars are usually at different distances, not clustered as they appear to be. Now, some are somewhat clustered. They're part of what's called associations. And Orion, in fact, the brightest constellation in the sky, it's the Great Hunter. Here's one shoulder. Here's the other shoulder. Here's the belt. Here's the sword. That's where the great nebula in Orion is that I showed you earlier. Here's one foot. Here's the other foot. Here's his head. That actually turns out to be what we call an association. Several of those stars were born, roughly speaking, in the same part of space and are moving, roughly speaking, in the same direction. But that's not true of most constellations, okay? And most don't look like what they're named after. Now, Orion happens to look like a hunter, and Scorpius does look like a scorpion to me. There's the claws, and here's the body wraps around like this and goes to the stinger here. There's the stinger. Don't get stung, So this one looks like a scorpion. Orion looks like a hunter. But most constellations are named in honor of the object, bearing their name, not because they happen to look like it. And, here's Leo the lion. It sort of looks like a lion. I'm starting to get more and more of a stretch. But this backwards question mark, that's the head. Goes down like that. then go out here to the body like that, and then the tail goes out to there. So that kind of looks like a lion. But most others, really are not that way. And in fact, the Big Dipper, though it looks like a dipper, is not even a constellation. It's what's called an asterism. It's a familiar-looking grouping of stars, which may be part of a constellation or more than one constellation. Usually a given asterism is part of only one constellation. But this is part of a much bigger constellation called Ursa Major, of course, the Great Bear. And if you can truly see a bear among these stars, other than the tail, then you either have a much better imagination than I do, or you're on some sort of weird stuff or something, which I don't recommend, okay? So, and the little bear, Ursa Minor, doesn't look like a bear either. But anyway, they were named in honor of bears and things. So we don't usually care very much about constellations, and this is why. Nevertheless, they're fun to learn, and there's mythology associated with them. For example, Scorpius the scorpion in Hawaiian mythology is not a scorpion at all. It's the demigod Maui who's fishing with his brothers, and they're going along in a boat, and Maui is dragging this fish hook in the water behind the boat, and he's lifting up the Hawaiian Islands as they're cruising along in the ocean. So that's what Scorpius means in their mythology, and it's not a scorpion, it's a fish hook. And it kind of looks like a fish hook to me. But anyway, you can learn about the mythology, and it's fun, it's interesting. You can learn about classics and Greek mythology by studying the constellations. But most scientists just don't care. Okay, except when showing, things to people and, trying to get a good date or something by impressing people with how much you know. And so we will discuss more later how the stars aren't all equal distances from us. They're at a variety of distances. But those distances are all so big compared to the radius of the Earth that just wandering around on the surface of the Earth, looking up at the sky, it's actually very difficult to tell stars are at different distances from us. So we say that all the stars are on what's called the celestial sphere. It's like a dome above you. And on a dark, moonless night away from cities, you especially get this feeling that you're in this dome, and the whole thing is rotating around you, and we're at the center of it. And it's natural for people to have thought that for a very, very large amount of time. But really what's happening is all the stars are way out there at different distances, but they all appear to be glued to the celestial sphere, and the rotation of the Earth about its axis once every 24 hours causes not only the sunrise and sunset, but the rotation of the entire celestial sphere around us. And so we see these stars rising, gliding over the sky, and setting. And what we see depends on where we're located. Everywhere on Earth, at any given time, the most you can see is half of the celestial sphere, that part which is above your horizon. So here's your horizon. It's defined by the plane tangent to the Earth at your position. And if the celestial sphere were nearby, you see that you would see only this part of it. But if you put the celestial sphere farther and farther away, you can see that the part that's visible approaches more and more the half of the full circle that I've drawn here, and by extension, half of the entire celestial sphere. And we will discuss what half we see at different times of the night and during different seasons when I return to this question on Wednesday. Okay, see you then. Thank you.